This is the fourth lecture of the lecture series on pericyclic reactions, and in this lecture I will focus on mainly 1,3-dipolar cycloaddition reactions, which is a very important topic, and photochemical 2+2 cycloaddition reaction, and also we will see how we can access beta-lactams, which is very important heterocyclic scaffold and found in numerous medicinal compounds and bioactive heterocyclic molecules, and we will see how we can access those beta lactams by 2+2 cycloaddition reactions. So as I say in the reaction in the beginning of the pericyclic reactions, that we are focusing on the cycloaddition reaction, and as we know, the pericyclic reaction involves the cyclic redistribution of bonding electrons through the concerted process, and therefore we don't need the intermediates to be formed in these reactions. That's why these are quite faster in rate compared to the other reactions. So we follow on the cycloaddition reaction of these several topics that can cover the pericyclic reactions. So in 1,3-dipolar cycloaddition reaction, as you can see here in the depiction, may I take the highlighter? Yes, okay then. So you can see this is the 1,3-dipole. We can see over here, and this pi bond, if comes over here, then the electron deficient positive charge can generate here, then that makes it the 1,3-dipoles. And in the 1,3-dipolar cycloaddition reaction, there has to have another component which is very important, and that is the dipolarophile. Okay, so 1,3-dipoles and dipolarophile, they make the cycloaddition reaction, and we get the 5-membered ring structure, and mainly these rings are 5-membered heterocycles. Okay, because it is very convenient or obvious that the 1,3-dipoles, when generated, one of the atoms has to be the heteroatoms. This is more likely the case. Similarly, it can be from with the olefin type of structures, it can be from the alkyne as well. So in that case, we can have the unsaturation inside the 5-membered ring structure in the product. So this can be the saturated 5-membered ring structure, this can be the unsaturated one. So depending on the dipole and the dipolarophiles, we can have different kind of 5-membered heterocyclic structures. And in this heterocyclic structure, mainly the 4 pi electrons comes from the 1,3-dipoles, and the 2 pi electrons comes from the dipolarophile. Okay, so this is the, it can be seen the 4+2 kind of pi addition reactions, and we can have the heterocycles. And importantly, that the HOMO of the dipole will participate in the reaction, and the LUMO of the dipolarophile will participate, and usually or most preferably the substrate will approach in parallel planes that will allow the interaction between the HOMO and the LUMO orbitals of the dipole and the dipolarophiles to give the better yield of the product, and definitely the products actually. So for that thing, this orientation of the dipole and dipolarophile is very important. Next, before we move, we will see some 1,3-dipoles, useful 1,3-dipoles. As you can see over here, there are several, and beside these exemplary examples, there are many more. The diazoalkane, you can see this is one example, and you can have the canonical structures of all these 1,3-dipoles. Azides are very important 1,3-dipole, which can help to form the triazole rings, which are very important in terms of synthetic perspective. Nitrile imine, it can be nitrile ylide, there can be nitrile oxide, nitrone, carbonyl oxide, and carbonyl ylides. So all these 1,3-dipoles are very useful, and I will focus on some of them when we talk about important examples and the synthesis and the example of 1,3-dipolar cycloaddition reactions. So I think I will not go into details of these canonical structures or resonating structures of these dipoles. These are quite easy and very easily understood, but the names and the types of the 1,3-dipoles need to be realized, and they are useful. I think it is when you know this is the 1,3-dipoles, then it gets easier to intercept the reaction or the product when it comes in the exams. So basically in 1,3-dipole, as you can see, if we are talking about the nitrogen atoms present into the 1,3-dipole and a olefinic structure is there, so basically that the reaction will proceed via this transition state, and you can see the development of partial charges on one terminal nitrogen and one on the terminal carbon center, and eventually ends up with a 5-membered heterocyclic ring structure and having the unsaturation. So we need to learn the key features of the 1,3-dipolar cycloaddition reactions. What are the basics for that? So first, from the transition state, we can see that the transition state is not very polar because there is no development of full charge or charge separation is there. Rather, this is only partial charges developed on either terminals of 1,3-dipoles, which is very likely. Secondly, as there is no permanent charge separation in the transition state, therefore the solvent polarity does not affect much in the rate of the reaction. So we can say that the reaction rate is not strongly affected by the solvent polarity. And in most cases, the reaction is a concerted process with pi4s and pi2s cycloaddition reaction, where pi4s is from the 1,3-dipoles and the dipolarophile provides the pi2s electrons. So this is that kind of cycloaddition reaction. And very importantly, it offers the route to the regio and stereoselective synthesis of 5-membered heterocycles. As 5-membered heterocycles, there are hundreds of thousands examples of 5-membered heterocycles which are biologically important and very significant in medicinal perspective as well. So importantly, that these reactions always are stereospecific with respect to the dipolarophile. This is very important, and you need to note the point or the feature because that can help in predicting the stereochemistry of the product and the chiral centers in the product. If we notice little bit regarding the orientation or the nature of the dipolarophile, and it have an usually a large negative entropy of activation, which is quite similar to the Diels-Alder reaction, that facilitates the reaction to proceed in a faster rate compared to the other reactions. So next we will move to see the reactions of dipolar cycloadditions and specifically the regio and stereoselectivity of these 1,3-dipolar cycloaddition reactions. So as I said that this is a very stereospecific reaction, and here you can see the diphenyl nitrile imine. This one is our substrate first, we can see, and with this cis-stilbene and trans-stilbene, the dipolarophiles, two different dipolarophiles in terms of their stereochemistry. You can see in the product, the red circle shows that the phenyl groups of the cis-stilbene are cis in the product. The stereochemistry is cis, and similarly, while the diphenyl nitrile imine reacts with trans-stilbene, we get the product, the 5-membered heterocyclic ring structure, and we get the phenyl rings in the trans orientation in the product as well. That directs that the reaction is stereospecific, and the syn addition happens with respect to the dipolarophile. We will see a couple of more examples here. The first one with the paranitrophenyl azide. As you can see, this paranitrophenyl azide reacts with this olefinic system, olefinic ether. So with this system, you can see the methyl and alkoxy groups. Those two groups are cis in terms of this olefinic structure or dipolarophile, and they remain cis in the product. Okay, so this is another example, and while we take the trans isomer, we see that the orientation of the methyl group and the alkoxy group are trans in relationship. So the syn addition precedes and stereospecificity of the reaction is established. Another example with the phenyl diazomethane being the 1,3-dipole and this olefinic ester being the dipolarophile, we can see the product structure, as I mentioned, that the stereospecificity prevails in the reactions. Okay, so two types of structures are possible. However, these two ester molecules or ester functional groups are always cis to each other, that centers. Okay. Next, we will see the highlight with N-oxide compounds, which are a significant example or substrate for the 1,3-dipolar cycloaddition reaction, and itself form a very good 1,3 dipole. And as you can see, the electron deficient center is formed close to the nitrogen center, adjacent to the nitrogen center, and O- that forms the electron rich center. And when an olefin comes, the terminal of that olefin terminal part and becomes the electron rich center, while alkyl group or alkoxy groups are attached with one carbon center. So that will react in the process in that shown here in this pathway, and we will get the fused 5-5 fused structure, where nitrogen atom is a part of the fused ring structure and the fused centers. And the stereochemistry of the 1,3 dipoles of the cycloaddition reactions will proceed by this way. Okay, so this is another example. We will see now several examples of 1,3 dipolar cycloaddition reactions, and by means of nitrones and nitrile oxide, because as I said that those are very useful 1,3 dipoles. First we will see how these 1,3 dipoles are obtained or synthesized. In the first reaction, you see with an aldehyde functionality, and a reaction with N-methyl or N-alkyl hydroxyl amine compound ends up with the nitrones, and if you use the hydroxyl amine itself, then definitely we will get the imine structure. And instead of this hydroxyl amine, if we use the N-alkyl or N-substituted hydroxyl amine, we will end up with the nitrones, which can be very useful 1,3 dipole. So if we use the simple hydroxyl amine, then we will end up with the oxime derivative, and from the oxime derivative, the shown pathway can lead to the nitrile oxide in the following pathway. As you can see, the treatment with molecular chlorine and further reaction with the base triethyl amine, we end up eventually with the nitrile oxide compound or derivative. While the nitroalkane compounds can be the substrate, while it reacts with the phenyl isocyanate, that can end up with nitrile oxides as well. So these are a couple of synthetic routes to achieve or to access the 1,3 dipoles itself. And now we will see how these 1,3 dipoles can react to give different products of very useful functional group or character. Here you can see this nitrile oxide reacts with a transalkene, and as I said, this is a stereospecific reaction. That means the alkyl groups or the substituent in the alkene will retain the stereochemistry or the relationship in the product as well. As you can see over here, this is the trans relationship with the substituent, and we get a oxazole ring structure. So, and this is the formation of the ring structure, and which eventually can open up. The ring opening can proceed by means of several reactions, like if we reduce with ranitidine and in presence of water molecule, we can get the alcohol, the keto alcohol compound, and with the two chiral centers, of course. And if we reduce by means of lithium aluminum hydride, we can obtain the amino alcohol compounds. So in all cases, you can see the relationship of the substituents remain the same even after the reductions, ring opening, and it can lead eventually for the formation of two important functional groups, amino groups and alcohol, the alcoholic group, that can eventually be used for further functionalization or lead to different products. So these are very fascinating things of nitrones and nitrile oxide in 1,3 dipolar cycloaddition reaction. Now we will see few examples. First one is a linear molecule with the terminal carbonyl compound. As you can see, when react with the N-methyl hydroxylamine, can end up with this the nitrile oxide compound, as you can see, the nitron compound, as you can see, and with the red circle you see the dipolarophile and the 1,3 dipole in situ or in the same molecule, and upon heating that can lead with a 5 and 6 membered fused heterocyclic structure. Okay, so this is one example. There is another one with diazomethane and the protected vinyl formyl compound or vinyl carbonyl compound, and that can lead up with to this heterocyclic ring structure as well. This is another one, and we can obtain from this reaction when it reacts with this the olefinic part, the 1,3-dipole with this dipolarophile. Eventually it can lead with this cyano-substituted oxazole compound. This is another another example of intramolecular 1,3-dipolar-cycloaddition reaction. It's been oriented or written in a way so it gives you to understand quickly, and upon heating you can have this heterocyclic ring structure, and upon reduction the amino alcohol compound will be obtained. So as the amino alcohols are very important class of molecules with very important functional groups, this 1,3-dipolar cycloaddition reaction lead to very fascinating class of heterocycles with very important functional groups in many cases that can help us to get different products. We will come with the 2+2 cycloaddition reactions. Here, as you can see, in under thermal condition, this 2+2 cycloaddition reaction is not allowed. However, under the photochemical irradiation, we can access this 2+2 cycloaddition reaction. So therefore, by means of photochemical irradiation, the reaction which was not thermally allowed, that can be made possible, and this symmetry incompatibility can be avoided by converting one of the olefins or the pi system into the excited state, and that can be done by photochemically. Okay, so you can see here the ground state of an alkene as you can see over here, and in presence of the ultraviolet light or photochemical irradiation in the excited state, the irradiation or the excitation can proceed like this way. One electron can move to the pi star in the low mode, so it becomes now the HOMO for the excited alkene. So by this way, combining the excited state of alkene with the ground state of another one, the symmetry problem can be addressed or resolved, and we can have the 2+2 cycloaddition products. Okay, so eventually by that means the alkenes can dimerize photochemically. There are several examples. The first one, while we will take the conjugated alkene and it absorbs the ultraviolet irradiation, and so this alpha beta unsaturated alkene or olefin can be excited. With the excited molecule, it can react with another simple olefin to give the cyclobutane ring structure appended with the carbonyl functional groups. Again, the other possible way that the alpha beta unsaturated carbonyl compound irradiated under ultraviolet light, and the olefin converted into the radicals, and those radicals can react with the olefin to give similar product with the cyclobutane appended with a carbonyl functional group. Another one very important point for this kind of reaction, that these reactions are stereospecific reaction. So an example for that, you can see here a cyclobutene substituted with two methyl ester groups, functional groups, and while react with a alpha beta unsaturated carbonyl compound substituted with a methyl group at 4 position, and when it reacts under photochemical irradiation, the reaction proceeds by this way, giving us a fused a tricyclic ring structure, 4-4-6 fused ring structure. And in that case, the most important point or trick that need to be remembered for the photochemical 2+2 cycloaddition reactions, that we need to look for the least hindered transition state, and that will be formed, and that will eventually lead to the product formation. So this is the tricky point regarding this kind of reaction, and also that this kind of 2+2 cycloaddition reactions are stereospecific. We will see some example of these stereospecific reactions now. For example, here, if the olefin is terminally substituted in one side, and it reacts with a alpha beta unsaturated ketone, and in that case we might end up under photochemical irradiation, we might end up with this kind of molecule instead of this one. So here you can see the this part is quite hindered, so olefin will not approach that way. Rather, this first way, this one which is photochemically allowed, and the olefin will approach like this way. One of the pi system will approach this way, and regioselectively we can get that product. So this is another example of regioselectivity of this kind of reaction. And there are another examples of photochemical 2+2 cycloaddition reactions where the pi systems are different in type. One is enone with olefin. We can see an example. This is the example that we see last, that we can have this 6,4 fused carbocycles, which in several steps caryophyllene can be obtained from these fused ring structures. So these are very important type of cycloaddition reaction. We must read that thing. There are another examples with alpha beta unsaturated carbonyl cyclic carbonyl compound with simple olefin, and we will get the fused ring structure, of course, in the major yield, the expected one, because there is no substitution, so there is nothing about the regioselectivity. However, the number of moles of the enone system is very important. In case you use more than 1 mole, then we can have these two isomers can be formed as well. In another example, one cyclic olefin with carboxy ester groups, and when react with the alpha beta unsaturated ketone compound as another pi system, so this these enones, while react with this kind of olefins with substituted olefins, end up with the fused heterocyclic fused ring structure 5,4,6 fusion, and giving us important tricyclic compounds. Now we will see some enones while react with allenes. So you can see with the allene system under photochemical irradiation can form this mixture of compounds with 2:1 ratio, and as I said, the late cinder side or the transition state will be preferred in these cases. And this is another example of two examples rather say of enones react with acetylene. This is an intermolecular version of that reaction, and where you can see this under photochemical irradiation, these fused cyclobutene ring structures formed, and they can eventually lead to the following tricyclic compounds, which are biologically very important. The another one with the intermolecular version with alkyne and enone system may lead up with this carbocyclic fused 4,6 fused carbocyclic ring structures, and these are very simple examples and easy examples, but these are examples of 2+2 cycloaddition reactions which occurs photochemically. And now I'm towards the end of this lecture. As I said that we will talk about the access of beta-lactams by 2+2 cycloaddition reactions, and first we will see some synthetic equivalent or synthones of these beta-lactams. As you can see over here, that ketene can be one component, and imine, substituted imine, can be another component, and from there on we can have the beta-lactam systems. We will see the example. There is another one that can lead to the olefin and substituted isocyanate compound. So those can be the synthetic the substrate which can be used to synthesize the beta-lactams in a 2+2 cycloaddition reaction. Now this first one, this ketene system, halogen substituted ketene system, can react with the imine and thereby giving us the lactam, beta-lactam compound or derivative with highly substituted functional groups with the aromatic groups and the halide groups. And another example of this isocyanate compound react with olefin, the classical example of a Staudinger reaction, where this olefin reacts with a isocyanate where the nitrogen atom is substituted with the sulfonyl chloride group and thereby giving the sultam ring structure, and this sulfonyl chloride group further can react in presence of sodium bicarbonate and water and converting it to the sulfonic acid, and then sulfur trioxide leaves, giving the beta-sultam derivative or the compound. So this is another example of formation of beta-lactams by means of 2+2 cycloaddition reactions through the formation or through isocyanate derivatives or isocyanate compounds as the substrates. So thank you very much for watching 3G Chemistry. Keep watching 3G Chemistry, and if you like the videos, don't forget to subscribe the channel and press the bell icon to have notification when I upload next videos. Thank you.